Get ready for significant, immeasurable opportunity in massive numbers. Scarab juice, the epic red Goliath star at the edge of our system, sends out tantalizing signals throughout the universe. Using the James Webb Space Telescope, cosmologists have made a remarkably shocking revelation about giant, godlike matter. Renowned astrophysicist Brian Cox issued a dire warning. A pressing question arises. Are we witnessing a cataclysmic cosmic explosion that could change the natural night sky forever? Let's dig into the details in the vastness of the universe, where stars live their fiery lives and finally die in spectacular displays. One star has recently attracted the attention and concern of scientists and the public. That star is Scarab Juice, a red supergiant of enormous size and age located in the constellation Orion. Its characteristic red color and variable brightness have long fascinated observers. However, recent developments have increased interest in this colossal giant. As we investigate the nature of Betelgeuse, we find ourselves on the brink of a potentially important event in the life cycle of a star. About several times the size of our Sun, Scarab Juice is a true celestial behemoth. Its incredible size is almost beyond human comprehension. Imagine a star so massive that if it were to replace our Sun, its surface would extend beyond the orbit of Mars and engulf Mercury, Venus, Earth, and Mars in its fiery embrace. This enormous size not only emphasizes the physical characteristics of Scarab Juice, but also marks its stage in the life cycle of the star. As a red supergiant, Scarab Juice is in the twilight of its existence, characterized by expansion and cooling after fusing hydrogen into helium over eons. As for the age of Betelgeuse, this star, estimated to be about 8 to 85 million years old, may seem humanly young, but it is ancient by the age of stars. Its current red supergiant stage represents the culmination of millions of years of stellar evolution, a period marked by dramatic changes and cycles that transformed it from a hot blue star to the red giant we see today. The life cycle of stars like Scarab Juice is a journey of change driven by the relentless forces of nuclear fusion and gravity. The distinctive red hue of the Betelgeuse is another sign of its current phase, as its surface temperature is relatively cooler compared to stars like our Sun. Scarab Juice's confusing behavior doesn't stop there. Its changing brightness adds another layer of intrigue. Scarab Juice is a semi-regular variable star whose brightness changes and fades in a distinctive dance that has fascinated astronomers for decades. But what really sets Scarab Juice apart is its incompatibility. Unlike some stars that follow predictable patterns, Scarab Juice sometimes deviates from its rhythm, suggesting complex and less understood processes within its massive structure. In a recent major development, Scarab Juice surprised astronomers around the world with an unexpected and dramatic change in its appearance. Now widely known as the Great Dim, in late 2019, this bright star began to mysteriously dim, losing brightness at an unprecedented rate until it reached its lowest brightness in February 2020. Betelgeuse, which is normally visible to the naked eye, even light-polluted areas were significantly reduced, a phenomenon that even amateur observers could detect. One challenge in watching Scarab Juice in action is the paradox of time. When we look at a star like Scarab Juice, we don't see it as it is now, but as it appeared in the past, because light takes time to reach us. About 725 light-years away from the Betelgeuse, the light visible today left the star nearly 7 centuries ago. This lag makes it difficult to predict and observe sudden changes in a star's behavior, since we are essentially looking at its past. The recent Scarab Juice blackout event highlighted the inherent challenges of real-time astronomical observations, as well as the difficulties presented by the enormous cosmic scales and the delay they cause. Andrea Dupree, director of the Harvard-Smithsonian Center for Astrophysics, and her team closely observed the events. They used the Hubble Space Telescope to study the giant star as part of a 3-year study to track variations in its outer atmosphere. These observations provided valuable insight into the dynamics of a variable star like Scarab Juice. Scarab Juice undergoes periodic pulsation and contraction, resulting in fluctuations in brightness, Hubble's sensitivity to ultraviolet light allowed scientists to study layers above scarab juice's surface that were partially heated by the star's turbulent convection cells. By analyzing Hubble spectra taken in 2019 and 2020, scientists were able to measure the movement of material in scarab juice's outer atmosphere. In particular, they focused on magnesium-2 lines, which provide clues about atmospheric conditions. These observations showed that material is moving from the star's surface to its outer atmosphere at about 200,000 miles per hour. This hot, dense material eventually extended thousands of kilometers from the scarab juice and preceded the formation of the dust cloud responsible for the dimming of the star. Dupree and his team estimate that during the explosion, about twice as much southern hemisphere material as scarab juice was lost over 3 months, a significant mass loss given that all stars, including scarab juice, have been steadily losing mass. Although much faster than our Sun, the sheer size of that explosion and the resulting dimming caused debate among astronomers as to whether it could be a precursor to a supernova explosion. The scarab juice's relative proximity to Earth, some 725 light-years away, adds to the intrigue, as any such explosion would be visible from our planet, offering a unique opportunity to observe a supernova up close. However, the question remains, what does this sad event mean for the future of scarab juice? Is this a sign of an impending supernova or just a unique episode in the long and complicated life of the star? Various theories have been proposed to explain this unexpected change. One popular hypothesis suggested a stage in the supernova explosion process, accelerated by the widespread belief that the scarab's juice was nearing the end of its lifespan. Another theory involved dust, perhaps from the star itself, obscuring our view. Scarab juice, like other red supergiants, can leak material that can form a dust cloud thick enough to dim the star's light from our perspective. The third explanation involved changes in the star's photosphere, or visible surface layer, that could affect its apparent brightness. A detailed analysis using different detection techniques solved this mystery. Spectroscopic studies showed a drop in the effective temperature of scarab juice, suggesting that the dimming may have been caused by a large dark spot on the star's surface. This hypothesis was supported by observations showing that the temperature of scarab juice decreased by at least 170 Kelvin during the darkening, suggesting massive changes to its surface. Ultimately, the key to understanding this surprising phenomenon came from humanity's cosmic eye, the Hubble Space Telescope. Hubble's observations showed that scarab juice's decline was likely caused by a massive ejection of hot material into space, forming a dust cloud that obscured part of the star's surface and reduced the amount of light reaching us. This dust cloud is thought to have formed from very hot plasma from a large convection cell on the surface of the star, which then traveled through the atmosphere into the cooler outer layers, where it cooled and formed dust grains, creating the observed cloud. Hubble's ultraviolet spectroscopic observations, which began in January 2019, helped piece together the timeline leading up to scarab juice's dimming, showing evidence of dense, heated material passing through the star's atmosphere 4 months before fading away. In December 2019, several ground-based telescopes also observed scarab juice decreasing in brightness, especially in its southern hemisphere. The ejected material, initially brighter than the star's
normal luminosity, eventually coalesced into a faint shadow as it spread outward and cooled. This outflowing material and the resulting shadow were thought to be the cause of the star's sudden dimming. The distance of this throw was staggering and brought scarab juice into the galactic spotlight. In a normal coronal mass ejection, the star ejects an estimated 400 times the mass. This mass, believed to be many times that of our moon, marked an important event not only for the Betelgeuse, but also for the understanding of stellar mechanics. This massive ejection of material has important implications for supernova theories. Conventional wisdom suggests that red supergiants like scarab juice continually shed mass before dying explosively. However, the magnitude of that separation casts doubt on this idea, suggesting a potentially violent and unpredictable final phase for these stars. Could scarab juice be preparing for its grand finale, a supernova explosion in the coming centuries? Recent research has speculated on the timing of such an event, suggesting that it could occur sooner than previously thought, perhaps within a few decades. Another important aspect of the scarab juice puzzle is the concept of spring shock. As a massive star moves through space at approximately 67,000 miles per hour relative to the surrounding interstellar medium, it creates a plume shock, similar to the wave produced by the bow of a moving ship. This phenomenon occurs when the outer layers of the star interact with interstellar gas and dust, showing the dynamic nature of the star and its interaction with the cosmic environment. The study of this bow shock not only sheds light on the current state of the scarab juice, but also improves our understanding of stellar evolution and mass loss processes. Regarding the recent behavior of scarab juice, observations show that its surface cooled and became less dense after the mass ejection, leaving the star in an unstable state even years later. Hydrodynamic simulations indicate a link between the star's convective activity, mass removal, and subsequent pulsational states.